So let's start our next presentation, a keynote presentation by Dr. Nick Kanopoulos from Brite Solar Technologies, Greece. So as we already have the screen ready, so yes, Dr. Nick.
Good afternoon, everybody. What I would like to present to you is how solar technology can be used for sustainable food supply, make a connection between the production of food and the support of renewable energies, specifically solar, to make the supply of food sustainable. Basically, the world is going to face extreme food pressure in the coming years because we expect to have 9.7 billion according to the UN by 2050, and in order to sustain to supply food for this many people, we have to increase production by 85% compared to today's levels. Which is a huge task because today agriculture accounts for 14% of the world's energy consumption and 70% of water usage. So it is very clear that in order to increase agricultural output at 80%, it's completely unsustainable because of essentially the water, energy, and food nexus. We have a lot more demand for energy. At the same time, there is a demand for food, and then of course the water, and all these three have to be balanced, especially water because 70% of water is used for agriculture. The climate change is in the middle of it, and it has a tremendous impact on agricultural production. And you can see many releases in the press for crops that are destroyed or crops that are affected because the yield is lower and the prices are rising because of that, and so forth. So in order to solve this problem, or a partial solution to this problem, is controlled agriculture in greenhouses. And the reason for that is that greenhouses yield 10 times more per square meter by using 90% less water. However, I apologize for that. I don't know why it's happening automatically. However, greenhouses need 10 times more energy. And this is the problem because in order to use this technology, we have to solve the energy problem. The energy in greenhouses, of course, is provided for photosynthesis of the plants, provide heat, controlled environment. And the question, then the natural question is, why not harvest the energy with solar plants, which is possible, but then we have to balance the piece, and I will explain what that is. If we see the solar spectrum has different regions, and these are the regions of the spectrum, and not all regions are equal as far as the growth of plants is concerned, and also the solar cells in producing energy. So the P1 is the part which is the photosynthetically active radiation, and the photosynthetic active radiation for most plants is from 400 to 500 nanometers, and then 600 to 650 nanometers. So the plants will require energy concentration in those wavelengths in order to grow. At the same time, the P2 is the power, and the solar cells convert photons into electrical power. Photons are absorbed, and however, all light is not equal to PV cells. If you see the absorption spectra for a solar cell, a silicon-based solar cell, in this diagram starts at 380 nanometers, going all the way to the infrared over 1100 nanometers. But the absorption curve is not really flat over this spectrum. So A photon can be used in this case for photosynthesis, for the plants to grow, and power generation, but it cannot be used for both things at the same time. And of course, in a greenhouse, we require for both of things. So we have the two P trade-offs: power and photosynthetic active radiation. So if we have solar light and we have a solar panel, and then inside a space like a greenhouse, there is a crop. If the crop is mushroom, then we can use essentially all solar radiation in order to convert it to power. However, if the crop is tomatoes that require a lot of light, then we can use only a very small portion of the solar radiation in order to be able to generate power and at the same time produce energy. So what is the solution? The solution is what we call PAIN power, is a transparent solar panel which has a uniform transparency over the entire visible spectra from 400 to 800 nanometers, over 80% transparent, and it utilizes a nanostructure coating that absorbs UV radiation, which is useless for both plants and solar cells to a large extent, and retransmits this light into the red region of the spectrum, specifically in the region between 600 and 650 nanometers where the plants photosynthesize, in order to facilitate the plant growth and compensate for the light blocking of the silicon solar cells in the glass. The glass transparency in this case is very high, over 80%, solar cell efficiency at 20.2%, and growing here, we can use right now half-cut cells at 22.2% transparency. And of course, we can vary the glass size and the level of transparency depending on what kind of greenhouse we are going to put it in, because there's no such thing as a standard dimension in a greenhouse. And at the same time, what kind of crop we are going to cultivate, because not all crops require the same amount of light in order to grow. The nanocoating material that shifts the spectra is a luminescent solar concentrator coating that we have developed. And this picture shows you the effect of the coating. So if you have coated glass and behind it a UV light, when the light is off, the glass looks like normal glass. But when the light turns on, then the glass becomes red because it absorbs the UV light and retransmits it into the red region of the spectrum. We made the measurement through a third party, namely Wageningen University in Holland, which is arguably one of the best agricultural schools in the world. And we certified that, in fact, when we have coated glass, then there is an 8% increase in the region of 600 to 650 nanometer of the light that goes through the glass. An 8% difference there means roughly almost half of that increase in the yield of the crops inside the space where this glass is a barrier to. We also have a second coating. The second coating of the same idea, but the second coating is targeting solar cells. The second coating absorbs UV light, but transmits it into the blue region of the spectrum, where the cells have quite a bit of room to absorb more energy and therefore increase their cell efficiency. So by combining these coatings where the solar cells are placed on the glass and where the glass has nothing in it, or where the light goes through for the plants, we create the green glass. which is a 4 millimeter thick glass system. It is either glass or glass PET, glass, 2 millimeter pieces of glass, and in between the coatings and the solar cells, or glass PET is glass plus plastic, 3.2 millimeters for the glass and half a millimeter for the plastic. We maintain 4 millimeter in thickness because that's the standard glass thickness supported by the greenhouse construction profiles. The glass is tempered, therefore it's safety glass for in case it's fractured for crops and also for worker protection. And we have custom sizing to fit customer structure and variable P1 and P2. So it's optimized for both, for power radiation and also for the power, depending on what kind of crops you cultivate in the greenhouse. To show the viability of this approach, we did some calculations as far as the economics is concerned in deploying this product in different parts of the world and for different crops. And in this calculation, we take into consideration what is the cost of deployment, and at the same time, what is the cost of electricity in those areas. And we come up with what is the payback time, and the payback time ranges from 5 years, which is in an area where there's not a lot of sun, to all the way to 2.5 years, like in Salinas, in California. An example of market implications for solar glass, and let's take a country where there are lots of greenhouses, Holland, for example. Holland has 9,000 hectares of greenhouses in today, and they have a 127% electricity consumption increase between the years 2010 and 2017 for supporting those greenhouses for lighting, automation, and mechanization. Assuming that all greenhouses are retrofitted with solar glass, then that will yield 3,600 gigawatt hours of electric energy, or 85% of all the electricity consumed by the greenhouses, or electricity consumption of 1.3 million Dutch homes, hundreds of millions of additional revenue for the crop growers, and 1.5 million tons avoided CO2 emissions per year, which is a profound sustainability and economic impact by using this approach. This is a pilot solar greenhouse done with such a glass. It delivers a negative CO2 footprint per kilogram of grapes, in this case produced, which is a global first in agriculture. Specifically, the CO2 footprint is minus 15.78 kilograms per kilogram of grapes, or minus 12.84 kilograms per square meter of greenhouse, or about 16,000 tons of CO2 avoidance per year. This is a dashboard that shows and this is a snapshot, of course, but this is something that we monitor in real time, and it shows in the installation of the glass what is based on the weather conditions that exist at the moment of the snapshot, because we have a weather station installed there, what is the energy produced, and the monetization of this energy based on the price of electricity paid by, in this case, by a winery in the local market, and of course, what is the CO2 avoidance for that day. A second application for that, which also contributes in a major way to sustaining food supply, is Agripv. In Agripv, we have essentially a support structure that protects the plants from adverse weather conditions, and at the same time manages the water supply to the plants. one of the biggest problems in open field agriculture is the great effect the climate change has on the environment, and thus extreme weather phenomena that destroy crops because of hail, snow, torrent winds, and of course you also have natural problems like birds eating soft fruit, etc. Here in this structure, we install this structure at an angle, and at the end of the installation, we have a gutter system, and then there's a vertical pipe at the end of the gutter, and all rows are connected to a central pipe. So what we are doing is we are collecting the rainwater while the plants are protected during a heavy rain. We collect the water, we put it in a storage facility, and then the farmer can use the water at the time needed and also at the quantity needed in order to water the plants. So in this case, with this structure, we generate energy, we protect the plants, and we manage the water, and therefore contribute towards solving the water, food, and energy nexus problem I presented at the beginning. I wanted to share with you the dramatic potential impact in terms of crop protection agri-systems in energy production and environmental impact. And I just took only one crop, which is grapes. Since Europe is the largest grape produced in the world as a continent, in 2018, we had a farming of 3,134,380 hectares for grapes, both table grapes and wine grapes. And if we assume 50% penetration or conversion of these fields to Agripv, just to make it dramatic, that is, then the energy production is 1,057,812 gigawatt hours per year, and the CO2 emission reduction is 677 million tons per year, and the energy revenues from selling the energy produced is over 42 billion, which is a fairly large number. In summary, the increase in food supply can be sustained without catastrophic environmental impact only if the required energy for this production comes from renewable sources. Solar energy is the best solution in this case because it allows for dual use of land, namely crop cultivation and solar energy production when transparent solar panels are used. And this is the technology we are pursuing and have been developing for a while and have been deploying in the field right now. Thank you, and I will be happy to answer any questions you might have.
Thank you for your presentation, Dr. Nix.